Hi, so this video is about parametric speed, but it also is an overall review and a couple of important comments. So I had in my notes from last school year that my students last year had some issues with calculator use at this juncture, and so I decided to include in this video a few comments about calculator use. So my first bullet point on the screen right now is just to make sure that you're all cognizant of the fact that there is an AP Calculus rounding standard. And it's not even as complicated as like in science when you have significant digits or something like that, sig figs. It's just way more basic than that. And so if you go to the decimal point and then there's the tenths, hundredths, and thousandths place, it's to round to the nearest thousandth if you are rounding. So if you're not rounding, you don't need to worry about this at all. So don't start saying, okay, my answer is 5, so now I have to write 5.000. That is not what we're talking about. We're saying if you indeed are rounding an answer, that you need to include the decimal point and then 3 digits after that, if you're rounding. Now, the 3 digits can either take into account what comes in the 4th decimal place, and you can round up or down based on that 4th decimal place, or what I actually would prefer and what I would coach you to do is just to truncate. Truncate just means to chop it off. So write decimal point, digit, 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 stop. Both the rounded version and the truncated version will be accepted. A version where you give fewer digits than that will lose you the answer point. The second point up here is to remind you, and this is something that I commented on in the previous video that I recorded, is that just because you're doing a parametric type question, something in the parametric context, doesn't mean your calculator has to be in parametric mode. You might be in function mode. So function mode is used to find where an equation is 0, where an equation is greater than 0, where an equation is less than 0. So function mode is definitely something that can be utilized regardless of what context the problem comes from. If you're just basically looking for an equation and like what's, like when is this equation equal to pi? That would be something you can do within function mode, right? You would graph the function, you'd graph y equals pi, see where they cross, for example. And deriv. I had some students last year who did not know that this was a thing, or, just had forgotten over the summer. So in the math menu, item number 8 is the numerical derivative. Now again, your calculator does not actually know calculus. So what it does is to take 2 points that are very, very close together. I believe the default is 0.001 units. And so it'll take 2 points that are 0.001 units apart and find the slope of the secant line between those. And that can be a useful tool just if you need to evaluate a derivative. So I just quickly put in here an example. So I'm in regular function mode. I have 5x squared. I want to find the slope of that function when x equals a particular number. So I can go into the math menu. I can pick item number 8. I want the derivative with respect to x of my function that is in the y menu. Y equals, it's my y1. I could certainly do that by typing in the equation itself, but if I already have the equation in my y equals, especially if it's a very cluttered equation, I don't want to have to type all that again. Are you kidding me? So variables, y variables, function, ta-da. Okay, and then come over here and say, I want to know the slope when x equals 2, for instance. Okay, it tells me the slope of that graph at x equals 2. I also can come back into my graphing menu and utilize this in a different but similar way. So still fill in x here, still fill in y1 here, but then say I want this for all x values. And then if I just do this on the standard window, it's going to give me a graph of the parabola and a graph of the derivative. And that graph of the derivative will come up kind of slowly. Usually not this slowly. Where is my derivative? Oh, there it is. This is really slowly. It will graph the derivative. Now, it doesn't give me the equation of that derivative, but it does let me visually see the derivative. Okay, so I hope that you knew that from math analysis, and if not, hopefully you know it now. I also wanted to point out in parametric mode, the calc menu can give you some more things. So let's go back. I had this example from the other video that I recorded in this unit. So you might recognize the graph. Oh, now I changed my window. Hold on. Okay, I was wanting to be able to see this a little bit better, especially if you're watching on a phone. Okay, so that was that parametric graph that was in the previous video. If you look in the calculate menu, look at this. Isn't this nice? You can find a value. You can find a slope. All of the first order derivatives are right in there. So if I had a question where I needed to find dy dt at a particular location, maybe I care about at pi over 4 for my parameter. It's going to tell me the slope, and it's also going to visually locate that for me. Nice, right? So I hope you're in the habit of when you learn new math, thinking, I wonder if this is on the calculator somewhere, because that's what you should do. You should look for things, and then you should teach your teachers where things are, because maybe we haven't even found it yet. All right, so the actual lesson. The difference between speed and velocity is a small but significant difference. Velocity is what we would call a vector quantity, in that it has a direction to it as well as an amount, okay? Speed is just the amount, so it's not taking into account direction. Other than that, these two things are really the same, but not really the same, because they're not the same, but same-ish, right? We talk about the speed, and then if we're talking about velocity, we say, well, it's the speed, but also taking into account if I'm going forwards or backwards or up or down or something like that. This little picture really is a very helpful little picture, okay? Look at this guy. So if you think about this as just like a little rate of change triangle, rate of change rate triangle, and think about, okay, horizontal rate of change, represent that on the horizontal, vertical rate of change, represent that on the vertical, then speed, since it is just an amount, not a direction, is the rate of change in that side of my little right triangle. And because you know Pythagorean theorem, you could just say, well, I know that dx dt squared plus dy dt squared would be speed squared. This is a little bit loose and free with the idea of length versus quantity, but close enough. And then if I want to get rid of this square, I would square root both sides, and then you come up with this. So I just think of this little picture, and I always can remember how I find speed in terms of parametrics. I'm going to look at the horizontal rate of change, I'm going to look at the vertical rate of change, and then it's basically just Pythagorean theorem layered on top of that. Now, something that I like to note at this point as well, just in my experience with teaching BC, is sometimes people are a little bit skittish about the word vector. Okay? Vectors in BC are like really no big deal, because they do, like, there's a lot to vectors if you actually study them deeply. If you ever take a mathematics class called linear algebra, so much about vectors, oh my goodness. So there's a lot that could be there, but BC calculus does not do all that, you guys. It's really, very, very chill. So when a question asks you about a position vector, a velocity vector, the word vector in BC life should just cue you to put two components together with a comma, and you can use fancy brackets if you want, but you don't even have to, right? A positions vector is just, where am I in terms of x, where am I in terms of y, put little brackets on it. Velocity vector, rate of change in x, rate of change in y, put the fancy brackets on it. That's it. You do not need to be so scared. That's it. All right. So today's lesson can be encapsulated by that red box that's on the screen right now. And I am going to, in particular, focus on just parts 1D and 1E big time. We'll do a little bit more than that, but 1D and 1E are the parts that are about speed. So I'm going to leave this up to you. If you've been feeling really solid on parametrics, I give you my endorsement, my permission, my blessing to kind of skim through the video until I get to 1D and 2E, and you need to watch those parts, okay? I'm just saying, all right? But, because that's the new bit. I will go through all the rest, so if you're not feeling so confident, you should full on watch the rest, okay? have a good time, right? I'm recording this on a rainy day. I hope you're watching it on a rainy day, not a nice sunny day. But if you are watching it on a sunny day, well, first of all, great, because it's a sunny day and that's enjoyable. But, you know, watch it as quickly as you can. Get it into your head so you can, like, get some outside time. I'm just putting that out there. Okay, we're going to do some math. I promise. I'll stop rambling. Okay, so in 1A, I'm going to remember the parametric definition of dy dx is dy dt divided by dx dt. I'm going to look here for my for my parametric equations that I need. I will take the derivative of y with respect to time and say, well, that's 2 cosine 2t. This 2 is because of chain rule. On the bottom, my derivative of cosine is negative sine. I notice that I have a restricted domain, so I only need to be thinking about this one time around the unit circle, so to speak. Okay. Then I'm going to come down here to the next part where it asks me about the horizontal and vertical tangent lines. BTW AC. This entire sheet is totally like mislabeled with things. I'm just putting that out there. Every year, like I've used this sheet before, every year I forget to fix it. Oh well. You can be flexible, I think. Okay, so why is it that I wrote that cosine of 2t has to be 0? Well, if I have a horizontal tangent line, that means my slope, my dy dx is 0. And if dy dx is 0, that means that this part has to be 0. And so if that part is 0, that means that part is 0. 2 can't be 0. The 2 in the front makes no difference. So it's really the other factor that has to be the 0. So I just need to know where cosine of 2t is 0. So I think about that, think about my trig life, and 2t is going to be at pi over 2, top of the unit circle, plus bottom of the unit circle, plus the top of the unit circle, plus the bottom of the unit circle, right? So that's pi units apart, so pi times n. And then because of this 2 over here, I'm going to divide through. When I divide through by 2, I get pi over 4, and then increments of 90 degrees, or pi over 2. So now if I substitute in those values of t into my original equation, I can find the x and the y coordinates that correspond to 3 pi over 4, 5 pi over 4, except from pi, you know what I mean? Like as you go around. So those ordered pairs, that's what I meant. Ordered pairs are these. And then root 2 over 2, 1, and then root 2 over 2, negative 1. Okay, if you just substitute in that part, you just like plug and chuck. Okay, that's not like highfalutin math, that's just evaluating. Okay, then the vertical part is going to be what happens when my slope is undefined, so this part is negative, which means that this has to be negative, which means that sine of, I just said negative, I meant 0. Sorry, let me try that again. So vertical is going to be when this part's undefined, which means that this part is 0, which means that this part is 0. Oy. Okay, so sine is 0 at 0, pi, 2 pi, etc. Okay, so actually, you know, I'm writing these in general, and I just remembered I had a restriction up here that just went through 2 pi. So you could have listed these out if you wanted to, right, instead. And this is going to stop. There's not going to be a dot, dot, dot. It's just going to be that. Okay, so the ordered pair part from the previous question is still the same, though. So I'm going to plug in 0 pi, 2 pi, see what ordered pairs I get. I get 1, 0, and negative 1, 0. Okay? Now, part D, I told you, is one of the things that we want to focus on because this is actually the new material, right? So here we are, important thing, okay, from today. And I'm going to think about the fact that I have that little triangle, and I'm going to remember that speed is that little Pythagorean theorem right triangle of speeds, of rates of change. So I'm going to take my two derivatives. My dx dt was negative sine of t, and my dy dt, and I'm going to square those and take a square root. So that's my formula for speed. So if I want speed at a particular time, it's again a plug and chug. See, this is actually not that bad of a lesson. I'm just saying, like it's really a formula. Okay, so I'd evaluate this at pi over 4. I'd evaluate this at pi over 2. Okay, so that substituting in would give me the square root of a half or the square root of 2 over 2, something like that, meters per second, depending how you wrote it. If you wanted a decimal there, like we talked about, you could have a decimal. Make sure you have 3 decimal places that are accurate. And same on the second part. You could have square root of 5, or you could round that to a decimal with 3 decimal places of accuracy. Okay, part E says to eliminate the parameter to write a rectangular equation. Okay, so in this one, I'm going to write down what my 2 equations were. So in green are the 2 equations in the problem, or I never know if I should call this 2 equations or 1 set of parametric equations. I think it's more precise to say 1 set of parametric equations because you need both of them to define the graph. Okay, so I'm writing down 1 set of parametric equations in green, and then in red, I've written down the identity that I think I'm going to make use of because I can see that both of these are mentioned like sine and cosine, and the red is a fact I can use to get myself out of parametric. So this cosine of t is equivalent to x. So I'm going to put right in here that this is x squared. Now I need something else for sine, but over here I have something that mentions sine. So I know that y divided by 2 cosine of t is sine of t. And then I'm going to do a little loop-de-loop thing here and say, well, x is the same as cosine. So I know that y over 2x is sine of t. And now I have something that gives me something parametric as related to something rectangular. And that was my goal. So in place of the sine of t in this identity, I can replace that with this rectangular form statement. And then I'm good to go. I could tidy that up if I want or not, because calculus, yay! Okay. I actually think I might just skip now. Oh no, we should do one that has a second derivative. Okay, we're going to do 2a. In fact, for 2a, what I'd like you to do is to write out those derivatives and come back and check your answer. And for 2b, I'd like you to do the same. I'd like you to write the equation of the tangent line. Tangent line, what do we think? I need a point and I need a slope. Okay, so I want you to do a and b, and then we're going to come back and do e together, and that's going to be it. This is getting a little on the long side, okay? So we'll do 2a and b and then come back and do e together. Try a and b by yourself now. Okay, I hope you tried these yourself. That's how you get practice. So 2a, you find the rate of change in x with respect to t, the rate of change in y with respect to t. Make sure you remember that this notation from trig world really means in, respectively, cosine of t quantity cubed and sine of t quantity cubed, okay? So you have to treat it like that, right? Use chain rule, bring the 3 down in front, keep the inside, take the inside to the second, and then multiply by the derivative of the inside. So that's where I got the purple and the blue. The green I have partially done. I'm taking the writing in blue and dividing it by the writing in purple. Okay, so when I set that up over here, is where I'm looking right now, I get very excited because I get to cancel some things because they make 1. So 24 divided by 24 is 1. Cosine divided by another cosine would be 1. Sine divided by another sine would be 1. I notice I have a negative here, so I'm going to make sure I don't drop that. And then all I have left is sine over cosine, which is tangent. So my slope is determined by the opposite of tangent of t. So then remember from Mr. Covey's video that the second derivative is found by taking the derivative with respect to t of my dy dx statement. And don't forget the critical piece of dividing by dx dt. So here's my dx dt statement. I need to remember what the derivative of tangent is. The derivative of tangent is secant squared, and my negative is just going to ride along. Okay, now I could rewrite this. Secant on the top is the same as cosine on the bottom, and the negative over the negative is going to make this all positive. So you might have it as 1 over 24 cosine to the 4th times sine in the denominator. Okay, you might not. Doesn't really matter. Okay. In this problem, if I need to write the equation of the tangent line, I need a point and a slope. So to get the point, I would plug in pi over 6 to x equals blank and y equals blank to find where x and y each are. Then I'm going to find my slope. So for slope, I need to use my equation from up above, which was opposite of tangent. And so I need the opposite of tangent at pi over 6. My stylus is acting up. So note something here about notation. This says slope. This part means at a certain value. That is the proper way to write it. You can also use English, right? Use the letters at, blah, 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 right? But I shouldn't just be saying dy dx equals sine negative tangent of pi over 6, because that would imply that the slope is always negative root 3 over 3, whereas it is not the case. This is just at a particular location that that's the slope. And so I'm going to write here my slope. I'm going to fill in here my point, and that is my point slope form of a line. Okay, the last question I would like you to try is number 1, part E. So this says find the speed of the particle at time equals pi over 4. We're still within the same question, so we're still using the same pair of parametric equations, okay? The same two that we were just working with, okay? Pause the video again and come back in a second. Okay, hopefully this worked out just awesome for you. You get a really pretty answer. You just need to substitute in for your dx dt and your dy dt. Make sure you square both pieces, and you should end up with the square root of 144 or 12. In terms of AP testing, this or this or this would all be acceptable answers. In fact, even this would be an acceptable answer because it's asking for a numerical value. If you think about it like a computer, all of those would do the same thing if they were programmed into a computer to calculate something. And so AP does not focus on the numerical simplification. That said, if this were, say, a multiple choice question, you would have to do enough simplifying to find the right answer, you know what I mean? But you have to love the free response portion of an AP exam because it does give you that flexibility to be a little sloppy, which is kind of fun. All right, the rest of this set of practice problems is posted on Schoology, so if you'd like to practice more, you sure can. But speed and those calculator tips are really what I wanted you to take away from today. Thanks.